Hey everybody, welcome to another video. In this video, we're going to talk about division of polynomials, and man, are we going to need that. In the next few videos, we're going to unpack something called Descartes' rule of signs, use that to simplify or make our lives easier with what's called the Rational Zeros Theorem. It's basically how to find x-intercepts if you have no idea what they are. So we're gonna start with long division of polynomials and synthetic division of polynomials because we're going to be using it so much in just a couple videos. So we're going to spend a lot of time doing that. But before we get to that, there's something I want to talk about called the factor theorem, and part of it is the remainder theorem. What just lets this stuff be possible? So I'm going to explain that. We're going to talk about long division and synthetic division. Why both? Because you need both. Synthetic division is super nice and it's very convenient and very fast, but it only works under certain circumstances. And so I'm going to teach you both of them because you will be using both long division and synthetic division in your math lives. So that's what we're going to be doing. So let's get right into it. What lets division of polynomials be possible is something called the factor theorem. And what we're going to be using is this idea that if you get a remainder of 0, what you're dividing goes into what you're dividing by goes into what you're dividing evenly and is therefore a factor. That's basically all of it in a nutshell. It sounds kind of wordy if you really just read it, and it goes, if upon division you get a remainder of 0, your divisor is a factor of your dividend. Here's what that means. Here's 48. Here's 6. And you go, oh, okay, let's divide 48 by 6. This is your dividend. This is your divisor. This up here is going to be your quotient. So we start dividing. You go, hey, does 6 go into 48? It goes in 8 times. You go, oh, 8 times 6 is 48. And if we subtract, we get 0. Oh, hey, the remainder is 0. And that's what this says. It says if your remainder is 0, then your divisor is actually a factor of your dividend. That means that you can factor your dividend as 6 times some other number. And that's exactly what we're going to be doing. That sort of summarizes the remainder theorem and the factor theorem as far as what you need to know to get this stuff done. So we're going to be doing a couple things. Number one, we're going to use the remainder theorem to say if you divide and you get a remainder of 0, this is combined with the factor theorem, then what you're dividing by is a factor of what you are dividing. We're also going to be checking this by plugging in a value and making sure that you get 0 out of it. That would say that you have this 0, which would create a factor for us, and then we can sort of use that in conjunction with our theorems to give ourselves a factored polynomial. That's what we're going to be doing. This is actually a good model for long division of polynomials, how it works. And so let's just jump right into it. Let's see, as we keep going, what this stuff means in relation to what we're doing. So again, why we're doing it, you are going to be doing this stuff a lot once I teach you about the Rational Zeros Theorem. You might hear Rational Roots Theorem. That is really important for us going forward with polynomials and also with rational functions. So here's how this works. The first thing that we're going to do is we're going to start testing a number to see if it's actually a 0. So here's the logic behind this. If I say, here's my polynomial, and I really can't factor it. So if I try to factor this, I might think grouping or something. Grouping's not going to work. I don't really have just a quadratic, so quadratic form is not going to work for us. There is actually a technique that you can go through to solve a cubic by just using the coefficients. That's possible, but it's really beyond the scope of like a pre-calculus level class. So you learn that much later, and it's very, very involved. So the way we get around that is by doing something called the Rational Zeros Theorem. And what it does, I'm going to kind of cheat here and give you a spoiler. What the Rational Zeros Theorem does is it gives you a list of numbers that are potential zeros for your function. All the rational, that's whole numbers, positive, negative, so integers, and fractions that could potentially be factors of your polynomial. So no, it wouldn't include square roots, things like that. But it's really, really helpful for us. So what that's going to do, that's going to have a list of numbers for you, and you're going to start trying them, and you're going to say, okay, hey, if something is a 0, an x-intercept, or a root of our function, then when I plug it in, it should give me 0. That's the whole point of being an x-intercept. So here's what we're going to do. We're going to take this value and we're going to evaluate it. If it gives us a 0, that means that this is going to create a factor for us. Think back to the last video. That's kind of exactly what we did. We said, oh, that's an x-intercept. Yep, and we can make a factor from it. Yeah, just subtract 1. You get x minus 1, and you know that's 2 videos ago. And you know that's going to be a factor. Well, that's using these theorems that we're talking about. So we're going to plug it in, see if it gives us a 0. If it does, we're going to divide because we know it's going to be a factor by these theorems. And then we're going to get a at least partially factored polynomial from it. That's awesome. Because in the last video, what we had was I gave you the polynomial already factored. I said, let's graph it. How do we get the factors? Like this, by dividing, long division or synthetic division. So here's our steps that we're going to go through. Number 1, we're going to check to see whether this x value is in fact an x-intercept. If you evaluate it and it gives you 0, then that's an x-intercept. Think about that. If I plug it in, it says you have a height of 0, then you are on the x-axis. That's what we're going to check first. After that, we'll create a factor and start dividing. So we're going to evaluate f of 1. So f of 1 would take and plug in 1 everywhere you see an x. And so we'd have 2 minus 1 is 1, plus 2 is 3, minus 3 is 0. Hey, look at that. If we plug in 1, we get 0. Here's what this says. What this says is that if you plug in 1 and you solve it, that is going to be your remainder if you were to divide the factor that 1 is giving you. Let me say this one more time. I'm going to evaluate 1. It's giving me 0. This right here is the remainder that I'm going to get if I divide the factor that this creates. So if I get 0, I have an x-intercept. That's what this is saying this is for sure an x-intercept, because when I evaluate it gives me 0. It gives me something on the x-axis. That's fantastic. Let's find the factor. So the factor would be subtract 1 on both sides. Oh, that x minus 1 equal to 0, that's using that sort of zero product property to say this thing is a factor. That's part of the factor theorem as well. This thing is a factor of your polynomial. Why? Because we know that our remainder is 0. Remember, if you divide something and your remainder is 0, then your divisor, what you're dividing by, goes in evenly or perfectly divides. Your dividend, you're going to get a remainder of 0. And so we're going to use that. So we're going to take our polynomial and we're going to do what's called long division of polynomial. And then I'm going to show you synthetic division after that. Synthetic division is much quicker, but it only works in certain circumstances. I'll explain that when we get there. So long division of polynomials takes your polynomial, the whole thing, and then it writes it where the dividend goes. So like where the 48 was in the first example. What you do need to make sure that you need to make sure that it's in order. That is very important. All our polynomials should be in order, but we need to be extra careful on that. Also, you need to have every exponent below your degree. Remember, your degree is the largest power of x. Below your degree, you need to have that represented. So if you're missing any, you put almost like a place value holder, like 0x cubed or something like that. We'll see that in the next example. Here we're not missing anything. So we're going to write the polynomial. And then we're going to write the factor that we're dividing. So one time all the way through, we are going to be checking to see whether this number creates an x-intercept. If you get 0, it does. After that, we're going to create a factor from that x-intercept. We know it's an x-intercept now, therefore it should work in the zero product property that when we multiply it, it's going to give us 0. So we're going to create a factor, and then we're going to divide our polynomial by that factor. This is factoring your polynomial, but not using a technique besides kind of checking a number to see if it's an x-intercept or a 0. Now, the question you should have in your head is, where'd that come from? Did you just randomly guess it? No, I didn't. This is going to come in 2 videos from now when I teach you the Rational Zeros Theorem. I'm teaching you this now, that way when we get there, we can immediately go for it. That's what this is for. So I'm going to go ahead, I'm going to write out my factor x minus 1. Now, please listen to something. I know for sure that this has to divide this already. Why? Because I plugged in the 1 and it gave me 0. It has to be a factor. So if I do all this work and I get not 0 down here, either I messed up on my evaluation or I messed up on my division. If you plug in this number and it gives you 0, then the factor that you create, it has to be a factor. Like it must divide this and give you a remainder of 0. 100% every time. That also means this. You're not going to waste your time doing long division if you check this number and it doesn't give you 0. So if you check it and it goes, oh, you got like 7. Why are you wasting your time? Because we're trying to factor polynomials. Now there is cause to do this sometimes. Sometimes you do need to divide things that are not going to divide evenly, especially like slant asymptotes, oblique asymptotes. You do have to do that. So I'm going to show that to you. But if you're checking to factor your polynomial and it's not giving you 0, you're done. Like you wouldn't go any further. So I guess the main point is, if you do this and you get this, it better divide evenly. If it doesn't, you've made a mistake. So here's how long division of polynomials works. What we do is base pretty much everything off this first term. So we're going to check our first term and divide by our first term. So 2x to the third divided by x. What's going to happen is that really all you're going to be doing is lowering that exponent and keeping that coefficient, because you're just dividing by 1x to the first power. It's not going to change much. That's the logic of how the synthetic division is going to be built. So synthetic division only works if you have firstly a linear. So like x minus something, not x squared, not x to the third, just x to the first power. And it also only works if you have your coefficient of x as 1. If that's not true, synthetic division does not work, or at least it doesn't work very well. Long division of polynomials, it's much more robust. It'll work all the time. So it'll work with x squared, or 3x squared, or 2x. Which is why I need you to learn both of them. So I need you to learn long division polynomials because you'll be using it to divide out x squared, quadratics, at some times. You'll be using it to divide out when your x is not just 1x. Or you'd have to change it and then use synthetic division. So and you can choose that, but you do need to know both of them. So with long division of polynomials, we take our first term and divide by our first term. If you need to write this off to the side, like, hey, 2x to the third, that's our first term, divided by x, that's our first term here. What we're going to get is 2 divided by 1 is 2, x to the third divided by x to the first is x squared. That right there is the first part of our quotient. We're going to put it right there. Now, just like every time you've done long division, we're going to multiply. Do you remember that? Like we divide, then we multiply, and we subtract. The same thing's going to happen here. However, when you have more than one term, you do have to distribute this. So we're going to take 2x squared times x. Well, that's going to give us 2x to the third power. And it should always be that your first terms here should be identical because you're subtracting and you need them to go away. And we distribute 2x squared times negative 1 is negative or minus 2x squared. This is the reason why you have to make sure that you have every potential power of x, 3, 2, 1, constant, at least represented in that dividend, because you're going to be matching up exponents, and if you miss a spot, you're going to go, where do I put this? And you go, I don't know, you messed it up. That's why we have to have that. Then we subtract, and this is where all the mistakes happen. Like 99% of them. And you know that, well, 95. You know this, right? Because I say this all the time, that 95% of your mistakes in math are probably sign errors, like mistaking negatives with positives. And that's what happens here. You see, when we subtract right now, we are really subtracting a polynomial minus another polynomial. Put parentheses around here. And when you subtract, understand that what you're really doing is 2x cubed minus 2x cubed, great, that's 0. But you're doing negative x squared minus negative 2x squared. Wait a minute. Negative x squared minus a negative. Subtracting a negative is adding. This sign, the second sign inside your parentheses, will always change. Always. So keep that in the back of your head. If you're always subtracting and you're distributing a minus, sort of, you're subtracting both these terms in this polynomial, your second sign is always going to change. So this says negative x squared minus negative 2x squared. No. Negative x squared plus 2x squared. Well, that's positive x squared. And we would bring down the plus 2x. Looks a lot like regular long division of integer numbers. And then we keep on going. So this is an algorithm. It's a process for doing this stuff. And we check the next term, so this first term divided by this first term again. So we take x squared divided by x. And if you simplify, x squared divided by x is 1x to the first power. Just x. Well, that's the next thing that we're going to put on our quotient. So since that's positive, we'll put plus x. And we're going to do the same process. We're going to take our positive, we'll think about this as positive x, and we're going to distribute. So x times x, that's x squared. It's looking good. Those are exactly the same. That's what we want to see. And we distribute x times -1. Well, that's negative x or minus x. And then just like before, we're going to subtract. So I'm going to put my parentheses around that because I'm really subtracting polynomials. So first minus second says x squared minus x squared. That's 0. That's what we want to see. We want to see those first terms kind of disappear all the time. But watch your signs. 2x minus negative x, and that's going to give us 2x plus x. Do you see? I hope you see why I use parentheses, because that's a little cue for my head to say, hey, slow down, you're going to have some sign changes. This second term is always going to change signs because you are subtracting. If you have more than that, all of your last terms are going to change signs because you are subtracting a full polynomial. So 2x minus a negative, so 2x plus x is 3x. And we bring down our -3. And we do this one last time. We're going to take our first term divided by our first term. And if we simplify, we simply get 3. And it's positive 3, so we'll put plus 3. If we distribute one last time, 3 times x is 3x. And 3 times -1, we think of that as -1, is -3. And if we subtract, this is pretty neat. This is what we knew would happen. Oh man, hey look, we should have a remainder of 0. This is what we knew would happen and what we wanted to happen, because when we get a remainder of 0, it says that what you've divided by, it's your divisor, divides perfectly into your dividend, gives you this quotient. In other words, this is a factor if you have a remainder of 0. It's a perfect factor. That's great. It means you can factor your polynomial. Fantastic. So when we subtract this, 3x minus 3x is 0. -3 minus -3. -3 subtract negative, so it's -3 plus 3, that's 0. If you do not end with that, either you've done something wrong, either this was wrong, or something happened here. So if you plug in this number and it gives you 0, and you create your factor by subtracting that number or adding that number if it's negative and getting this factor, this has to divide that and give you a remainder of 0. If that doesn't happen, something went wrong, or if you didn't get a 0 there, then why are you doing this if you don't absolutely have to? Sometimes you do, but for finding factors, you wouldn't. You'd want to make sure, right? You don't want to check, do long division on every potential factor. That's crazy. It's going to take you forever. So we find the factors, we find the values of x that give us 0. We create our factors, and we know that they're going to be factors. That's what we're going to be doing in 2 videos from now. Now, why? Why does this even matter? Well, here's the reason why it matters. Because if we know that we have a remainder of 0, we can now rewrite this polynomial that we did not know what its factors were. We didn't know how to graph it, and now we can rewrite it. And we know for sure right now that, hey, this dividend is now a product of a factor. We know it's a factor. It has a remainder of 0. And the quotient. So we could write it as x minus 1, 2x squared plus x plus 3. Now, what would you do now? Well, that's a quadratic. You could try to factor it further. You could try a quadratic formula, but if you do that, your discriminant is negative. It says that's an irreducible quadratic. Check it if you want to. Pause the video, check it. Try the quadratic formula. You'd get b squared minus 4ac, and that's going to be negative. There's no x-intercepts. That's saying irreducible quadratic. That's fantastic. If you do quadratic formula and you get I, or a negative inside your square root, you have an irreducible quadratic. You can't factor it. You're done. This is completely factored over the real numbers. That means that you had really no idea what was going on here besides that's a positive cubic, so it should look like this. It should have at least one x-intercept. Think about that. If your graph looks like this, here's your leading term, Here's your degree, max turning points of 2. That's a positive odd, looks like this. That means that you have to cross the x-axis. Well, you know what? We just found it. We cross the x-axis at x equals 1, multiplicity 1. It is a cross, and this is an irreducible quadratic, and we have no more x-intercepts. That's pretty neat, but that's the reason why we need to learn how to divide so that we can get this far, so we can understand, oh, okay, that's really what this graph is going to look like. It probably has another turning point, but it's not one that causes a different x-axis intersect. So we're done. That's about as much as I need you to know. So we're plugging in a value. We're making sure that we get a 0. If we do, cool. We create a factor, we divide it, and we write this as a factored polynomial. Can you continue past this? Yes, but you need to try another x-intercept. In our case, we had a quadratic, and you go, let's just do quadratic formula, because that's easier than guessing and checking. But if you had like a power 4 still, power 3 still, you'd need another x-intercept to create another factor. And that's the whole process in 2 videos. We're going to have a list of numbers. We'll get an x-intercept, create a factor, divide it. Find another x-intercept, create a factor, divide it. We keep on going. Now I'm going to show you synthetic division. It's really cool. I mean, it's really, really useful. But there are some special circumstances that you have to have. I already explained it, but I'm going to go through it one more time. This is what you have to have. Number one, you have to have that your divisor has a 1 in front of your x. Honestly, you need to basically solve for x. I'm going to show you this in just a second. You want this to be x equals some sort of a value. It can be a fraction, that's okay, but you need to have solved for x here, basically. Second thing, you need to have every single one of these exponents of x represented just like you did for long division of polynomials, and that's pretty easy. So here's the way that synthetic division works. We're going to use just the coefficients of our polynomial, and we're going to put them right here. So we're going to say that our coefficients are 2, -1, 2, and -3. We include the constant, even though it's not a coefficient, we include that. And we leave ourselves a space right below. Then what we do is we take the x-intercept, 1, not -1. I see so many students make that mistake and they go, oh yeah, you get your factor and you do this, so you're going to put -1 here. No, synthetic division is very special. Synthetic division, when you divide it, has the special circumstances so that you can just take this value and divide with it. So we're going to take 1. We're going to use 1 as the thing that we're dividing with synthetic division. So we just put our 1 here. So you take the x-intercept, not the factor. The factor is used when you're actually dividing. That's what we're doing. We're taking the factor divided by the factor. But with synthetic division, you don't do that. You take what x equals. This is why I started this way. This is why I said this is what we're checking. This is the x-intercept. This is what you divide by. If you make and put -1, you're going to run into a whole lot of issues, and you're going to get very frustrated because you go, never works. Darn you, Leonard. Hey, it ain't me. Make sure that you have the x-intercept there. And here's what we're going to do. It's a process, it's an algorithm, it's extremely fast. We bring down the first coefficient. So we're going to bring down the 2. Oh yes, I forgot the other special condition. With synthetic division, you have to have solved for x, which means you cannot have x to the 2nd power here, or x to the 3rd power. Synthetic division works as you've solved for x completely. X equals a constant, and that's what you're dividing by, right? So if you don't have x to the 1st power, you haven't solved this yet, and therefore you can't put that number there unless you've solved for x. So this is a very special case thing where you have x to the 1st power equals an x-intercept. It's just for x-intercepts, and it gives you a factored version of it in just a minute. So that's what we're doing. Just make sure that you've actually solved for x and you're set. So we have x equals 1, we put the 1. We bring down our first coefficient, we put 2. And the whole process, the whole algorithm is multiply, put it here, add. Multiply, put it here, add. Multiply, put it here, add. And this will be your remainder. The last number you get is your remainder. So let's go ahead and do that. I'm going to now multiply 2 times 1. I'm going to put it right here. Then when I add, I'm going to get 1. I'm going to multiply 1 times 1. and I'm going to put it here. 1 times 1 is 1. And then I'm going to add. Well, 2 plus 1 is 3. I'm going to multiply 1 times 3. Well, that's 3. I'm going to put it here. When I add, notice you're adding here, you're going to get 0. This last piece is your remainder. Well, wait a minute. That 0 is exactly like that 0. That's your remainder. We knew we had to get a remainder of 0. That's what we did when we checked for an x-intercept at the very beginning. Now, this might look like just gobbledygook, but that right there are the coefficients of your quotient, 2, 1, and 3. So, because we're always dividing by x to the first power, while dividing by something that's equal to x to the first power, really what we're doing is we're just lowering our exponent of every term by 1. And what that means is that no matter what you do here, you just look back at your original, you go, okay, because I start with x to the third power, and I'm practically dividing out an x to the first power, what I'm going to get is lower all of these by 1. This would be 2x to the second power plus 1x to the first power plus 3. Well, that 3 doesn't have an x to a power because that's a constant. That right there is your quotient. And this is pretty cool. It's pretty cool because we got the same exact thing as this. We got our quotient, but we spent a whole lot less time on it. And that's not just because I was explaining this fully. It's because that's much quicker. But for certain circumstances, again, that will not work if you're trying to factor out quadratics, and this will, which is why you need both of them. So the last thing we would do is say, all right, we're going to go ahead and factor our polynomial like we did over here. We know that (2x squared plus x plus 3 is part of it. That's an irreducible quadratic. We already explained that. But now I have a factor, and this is the second place where some students can get confused on this. So keep this in mind. What you did right here is you set and found an x-intercept of 1 and used that 1. You need to make sure that you subtract 1 to find your factor. You can see this, right? That a lot of students go, oh yeah, my factor is x plus 1 because that's positive. No, it's opposite of that sign. So think back to what you're doing. This right here gave you that number. This right here is not your factor. You have to subtract 1 to get that factor. So our factor is x minus 1, and that's exactly what we got here. Which one do you do? Which one's better? Honestly, I'm pretty quick at this, and I never make mistakes with signs because it's right there. So I actually prefer this, and it works all the time. But don't let my opinion influence what you choose. A ton of people love this because it's extremely fast. I'm going to be doing both of them pretty much all the time, just so you can get good at it, and I want to always reinforce the concept. So you're going to be seeing long division of polynomials, and you're going to be seeing synthetic division. It doesn't take that much longer for me to show, and so I'm going to always do that for you, just to get you prepared. You even use long division in calculus, like Calc 1, Calc 2, Calc 3 on occasion, where you have to divide a polynomial by something. And sometimes it's useful to divide it even if you know you're going to get a remainder that's not 0. So we have 2 more examples to do. The next one where we're missing some exponents, and the one after that where we don't have a remainder of 0, and just what you do with that. This would be like a for later sort of an idea. So I'll see you in a second. All right, let's keep on going, shall we? So we have a honestly really nasty polynomial there, and we're going to try to factor it as much as we can, or at least we're going to get 1 factor out of it. And then we're probably going to stop because it would take a long time to keep on going, but this idea is important. However, I have not taught you how to get the list of numbers, so we'd have to really guess and check to keep on going after this. So we're going to try to factor that thing. Now, before we get going, if you have a degree 5 or higher, there is no general way to factor that by using the coefficients. So there's no formula to plug in to factor that thing. You have to know something about this function in order to factor it. That's where the Rational Zeros Theorem is going to come in about 2 videos. I know I'm kind of playing it up, so that way you'll have to watch it. But this is what would happen. You'd have a list of numbers, and you would say, all right, which of those are x-intercepts? So you plug them in. You go, I'm going to plug in something easy like 1. Does it work? No, 3 plus 82 plus 27, that's not 1. Or that's not 0. Plug in -1. No, that's not going to work either. And eventually you get through your list and you get to something like -3. So that's where this would come from. I'm not making it up. I'm not really guessing at it. I would have a list of numbers given by a technique I'm going to show you in 2 videos that would give that to you. And so here's our job. Once we have that, we go, okay, I'm going to check -3. We're going to plug in -3. We're going to evaluate this, and we're going to see what it gives us. If it doesn't give us 0, then that's not an x-intercept, and it will not create a factor for us. If I evaluate for -3 and it does give us 0, think about that. Evaluate something, it gives you 0, you're on the x-axis. It is an x-intercept. It will give you a factor. And then we keep going, and then we divide. So that's the process of doing this. That's what we're going to get to in just a couple videos. So let's evaluate g of -3. So, did this already. That's pretty hard to evaluate. You're definitely going to want your calculator because -3 to the 6th power is already pretty big. And then you multiply by 3, add 82 times -3 to the 3rd power and 27, and you are actually going to get 0. So we'd spend the time to do that and we'd say, hey, because I evaluated -3 and it gave me 0, I know a couple things about this function right now. Number one thing I know is that that's an x-intercept. Now that's fantastic. You go, why don't I just stop there? Because that could potentially have 5 more. And so you're going to want to know what this function looks like in order to figure out more x-intercepts. Now, what should this give you? If I start dividing by x plus 3, which is a factor, it should give us 2 things. Number 1, a remainder of 0. Number 2, it should give us some degree 5 polynomial. Remember, I have x to the 6th. I'm going to be dividing by x to the 1st. It should give us a degree 5 polynomial as a quotient. And that's important to understand that. We're just going to be lowering the degree by 1. That means we could potentially have 5 more x-intercepts to find. And so that's the reason why we don't just end here like, hey, I'm good. We have to keep going to give ourselves some quotient to see what's next. If you go, well, why don't I just try all the numbers on this apparent list that you're going to give me and just be done with that? Well, because the list is only rational zeros. It won't show up any square roots, so any radical zeros or other types of numbers. And so it is important for us to be able to use this to get a polynomial that we can do further work with. That's why we're doing it. There's not really a great way around it. And so here's our thought process. We plugged in -3, we evaluated that, it gave us 0. It says this, that's an x-intercept. We know that if we have an x-intercept, we did a few videos ago, that I can set this equal to 0 by adding 3. And x plus 3 is a factor. It has to be a factor of that polynomial, and it has to give us a remainder of 0. This is what our remainder should be. This is what we're going to get when we divide. So we're going to put x plus 3 where we put our divisor, and we're going to put our polynomial inside of our division symbol. It's where the dividend goes. And so what we're going to be doing, though, is we're going to make sure that we have a power of x for every potential exponent less than 6. So 6 is our degree. We're going to start with that. But we have to represent the 5th power, the 4th power, the 3rd power. It's there. 2nd power, 1st power, and then our constant. It's there. How we do that is with a 0. So we'd say 0, x to the 5th. It's kind of like a place value holder. 0, x to the 4th. We actually have an x to the 3rd. We don't have an x squared or an x, but we do have a 27. And so we now have, let's make sure, 6, 5, 4, 3, 2, 1 constant, and we filled that out completely. It looks pretty tedious, and honestly it is. There's a lot of work here. We're going to have lots of steps. I'm going to go through them fairly quickly. Man, you should be doing the same thing on your own, all right? We really should be checking this along with me. So what we do, though, is basically the same thing we did in the last example. Take your first term and divide by x. That's always our first term. If our first term is not just x, this will still work, even if you have a quadratic or something like that you're trying to divide. So 3x to the 6th divided by x is 3x to the 5th. I'm not going to be writing this off to the side. I'm doing this in my head. 3x to the 5th times x, we're going to get 3x to the 6th. We distribute and we get 9x to the 5th. Now, I always put parentheses around it because we're subtracting, and I know that when I'm subtracting polynomials, my signs change. So 3x to the 6th minus 3x to the 6th, that's 0. 0x to the 5th minus 9x to the 5th, not plus, minus, your sign changes. That's negative 9x to the 5th. And I bring down my 0x to the 4th, and I continue. Then we start with our next first term. So negative 9x to the 5th divided by x. Basically, you're just subtracting one from the exponent. That's really all you're doing. That's negative 9x to the 4th power. So I'm going to put minus. And then I'm going to distribute, make sure you distribute with your sign. Negative 9x to the 4th times x, well, that's negative 9x to the 5th. That's fantastic. We're always checking this. If that's not the same, we've made a mistake. Negative 9x to the 4th times 3 is negative, so I write minus, 27x to the 4th. Double checking my work. Okay, I know that's right. Now I'm going to subtract again, keeping in mind that when I'm subtracting polynomials, my signs change in my parentheses. So negative 9x to the 5th minus negative 9, that's 0. 0 minus negative 27, that's positive 27. And I bring down my next term. And again, we start with our first terms, 27x to the 4th divided by x. Well, I'm basically just subtracting from my exponent because my coefficient is 1. 27 divided by 1 is 27. And x to the 4th divided by x to the 1st, you subtract exponents, you get to the 3rd. And that's what synthetic division is kind of based on anyway. But here I get positive, so 27x to the 4th divided by x is positive 27x to the 3rd. And I distribute. So 27x to the 3rd times x is 27x to the 4th. 27x to the 3rd times 3 is 81, so positive 81x to the 3rd. I hope you're seeing the reason why we had to have a place value for every potential value of x. Otherwise, we would have nowhere to put that. Where do I put it? I don't know. There's no spot for it. That's why we had to have that. So I'm keeping in mind that when I subtract, all my signs change inside my parentheses. That's why I put my parentheses. 27 minus 27 is 0. My exponents match up. That's fantastic. 82 minus 81. Remember, we're subtracting positive 81. That's 1x to the 3rd. And I bring down my 0x squared. X cubed, that's our first term, divided by x, that's our first term of our divisor, is x squared. Positive x squared. When I distribute, we get x squared times x is x to the 3rd. X squared times 3 is 3x squared. We put our parentheses, we do our subtraction. We're getting a little tedious here, but that's okay. It's going to work out well. X cubed minus x cubed, that's 0. 0 minus 3. Remember our sign shade. 0 minus 3 is negative 3x squared. And I bring down my 0x. We actually know it's going to work out because we already checked it. So that's kind of cool. That's encouraging that we know what we're going to get. And we take our first term and divide by the first term of our divisor. So negative 3x squared divided by x is negative 3x. So we put minus. Then we distribute. Negative 3x times x is negative 3x squared. That looks great because it matches up with our first term. That always has to be the case. And negative 3x times 3 is minus or negative 9x. We put minus 9x. And we subtract. Our signs are going to change. Negative minus negative. So negative 3 minus a negative is 0x squared. 0 minus negative 9. Well, that's 0 plus 9. That's 9x. And bring down our 27. It's exciting. 9x divided by x. Hey, those x's would cancel. You just get 9. When we multiply, 9 times x is 9x. 9 times 3 is 27. When we subtract, 9x minus 9x is 0. 27 minus 27 is 0. We know what we should have got, 0, and now we've confirmed that we got it. So we're for sure that we have this stuff all correct. That's why you go all the way to the bottom. Plus, you figure all these coefficients and constants anyway. So this is what this says to us. This says that this polynomial has a factor, and this is what's left over after you factored it out. So in other words, run out of room to write this. Get your function name right. We have x plus 3 as one factor, that's a linear. And then we have this power 5 polynomial, 3x to the 5th minus 9x to the 4th plus 27x cubed plus x squared minus 3x plus 9. Now, are we done? We are done. But what would happen later is that you would have some more numbers on the rational zeros list that you would plug into this power 5 polynomial to see if it gave you an x-intercept. To see if you evaluate, it gives you 0. That means you're dealing with an x-intercept. That gives you a factor, and you would redo this until you got down to 1 or 2 types of factors. Linears, or power 2s that the quadratic formula does not work for. In other words, it gives you complex numbers. That's when you're done. So if you have a power 5, I guarantee you there's at least one more x-intercept. Why? Because it's an odd. That right here is an odd function. It has to cross the x-axis one more time. It has to, not just bounce, cross it. There has to be a cross there. So this would not be fully factored, guaranteed. We're not going to spend the time to find the other x-intercepts because we don't have that list of numbers and I haven't taught you how to do it. That's not this video. But just understand that once you find, this is the process here is for you to understand that once you find an x-intercept, you get a factor and you divide it. Now we're going to do synthetic division. It's much, much quicker. You're going to really like it here, and then you'll see that, that we get the same thing. So let's write it out. How we do it is basically the same as this, but you don't include any x's. So you still have to have all of those coefficients. So you look at your polynomial and say, all right, there'd be a 3x to the 6th. Then you have no x to the 5th and no x to the 4th. You have a 82x to the 3rd. You have no x squared, you have no x. And you have 27 as your constant. We know that our remainder should be 0. Let's make sure that happens. So what we're going to do is we're going to do synthetic division here. It is a little bit different than long division because you don't take the factor, you take the x-intercept and use that in the algorithm. So we're going to take -3. Now, when we go ahead and do it, the first step is to bring down your first coefficient. So we're going to bring down the 3. The reason why that works is because with synthetic division, you always have to have x that's solved for, so no coefficient. So basically, you're counting on that you're dividing a first term by 1x to the first. It's just lowering your exponent by 1, and it's keeping your coefficient. That's why that works. Now we're going to multiply and add. Multiply and add. Multiply and add. So bring down the 3. This is -3 times 3. That's -9. Add 0 plus -9 is -9. Multiply -3 times -9 is 27. 0 plus 27 is 27. Multiply -3 times 27 is -81. Add, you get 82 plus -81 is 1. Multiply -3 times 1 is -3. And add 0 plus -3 is -3. Multiply -3 times -3 is +9. Add 0 plus 9 is 9. Do you see it? That's exactly the same coefficients that we have there. Multiply -3 times 9 is -27. If you add 27 plus -27 is 0. Go to the end, make sure you have a 0 there. If you don't, if you did this right here and it says you do have a 0 and you don't get it there, something happened that was bad. And now the last thing we would do is understand that you're dividing out x to the first power. You're just going to take all of those exponents and subtract 1 from them. That's what your dividing out does. Dividing exponents, you subtract. So we'd have 3x to the 5th minus 9x to the 4th plus 27x to the 3rd plus 1x squared minus 3x plus 9. And everybody agrees that that's way faster. And that's fantastic. Do it all the time if you want to. Just when you can't do it, it's nice to have something that works for like quadratics and things of that nature. So this would be exactly the same as what we have right here. We'd say, hey, that's our quotient. We know what a factor is. A factor would be, that's an x-intercept. Never forget this. This is not x minus 3. This is x equals negative 3. Therefore, x plus 3 equals 0. Your factor is x plus 3, not x minus 3. That's the same exact factoring that we've got right here. So either way you want to go on that for now. Again, I'm going to be doing both. That's obviously a lot quicker. I have one more example what to do if you don't have a 0 but you still need to divide. So hang on for that one. Okay, one last example of what to do if you don't have a remainder of 0 but you still need to divide, what you do with that remainder. I want to bring it back a long time ago. What happens if you were to divide 49 by 6? You go, well, it doesn't divide. You're right, you're going to get a remainder of 1 actually. So 6 goes into 49 8 times. If you multiply, you get 48, and if you subtract, you get 1. And that remainder of 1 creates a fraction. If you divide, it goes into 49 8 whole times, and you get 1 over 6. Or in other words, your remainder over your divisor. And this can be added to it. 8 plus 1/6 is 8 and 1/6. That models what we do with a remainder that's not 0. So I'm going to show you that right now. So let's first check to see what the remainder is. So you go, hey, x is 2. That's on my list. And so here's my polynomial. Here's a number that I'm checking. So I figure out what happens if I evaluate 2. So I plug in 2 and I go, all right, let's see. 2 cubed is 8. 8 times 4 is 32. 2 squared is 4. This is 12. 32 minus 12 is 20. Minus 16, that's 4. Plus 4 is 8. You go, oh, great. I'm going to get 8. Yay. Wait, is that an x-intercept? No. Because if it was, if you evaluated it, x-intercepts give you 0 on the x-axis when you evaluate them. So this is clearly not an x-intercept. What that means is that x minus 2 is not a factor. If I divide this polynomial by x minus 2, it is not going to divide evenly. I will not be able to write it as a factor. But I can write it as a quotient plus some sort of a remainder. And so that's what I'm going to show you how to do. Sometimes you have to do this. It's not often, but sometimes you do. So we're going to write 4x cubed minus 3x squared minus 8x plus 4. There's no missing exponents. That's kind of nice. I'm going to take the potential factor we know it's not going to be, and I'm going to divide it. I'm going to go very quickly here. So 4x cubed divided by x is 4x to the second. That would be 4x cubed minus 8x squared. When we subtract, we need to make sure that our signs are changing our parentheses. This could give us 0. That's great. Negative 3 plus 8 is 5x squared. I'm going to bring down my minus 8x, and we're going to do the whole thing again. So 5x squared divided by x is positive 5x. I'm going to distribute 5x squared minus 10x. So 5x times negative 2 is minus 10x. I'm going to make sure that I have my parentheses, because when I subtract over parentheses, my signs change. 5x squared minus 5x squared, 0. Cool. Negative 8 minus negative 10, that's 2. And lastly, 2x divided by x is 2. I'm going to put 2. 2x minus 4. And you go, oh, that's 0. It's not 0. Because when you subtract, 2x minus 2x is 0. That's great. But 4 minus negative 4 is 8. That says we have a remainder. Wait a minute. That's exactly what that is. Exactly. That's great. That's fantastic. It's what we wanted to happen. We knew that it was not going to factor well. That's not a factor of this. So here's what you do with it. Much like the 1 over 6, the remainder over your divisor, You take this, if it's positive, you write plus, if it's negative, you write minus. So here we write a plus. Your remainder over what you divided by. And that's how you can take and divide a polynomial by something that's not a factor and still write something relevant. This is useful on occasion when you get to something like Calculus 2. Sometimes we have to do this to do some integrals and make things a little bit easier. You end with an, if you did this, you end with the integral of ln x minus 2. But that's way beyond where we're at. I'm just letting you know this is what you do when you get there. So if you don't have a remainder, honestly, if you plug that in, it doesn't give you 0. In this class, you're pretty much done. But if you have to do it, then this is the way you go and do it. You have a remainder, you put, if that's negative, it would be a minus here, minus 8 over x minus 2. Okay, synthetic division is very, very similar. We take our coefficients and our constant, 4, -3, -8, and 4. We have no missing exponents, so that's cool. And we take what x is equal to, not our factor, but what x is equal to, our potential x-intercept, and that's 2. And then we go ahead and we do our synthetic division. Synthetic division, based on the factor divided by x to the first power, brings down your coefficient, multiplies, 4 times 2 is 8, and adds, -3 plus 8 is 5. Multiplies, 2 times 5 is 10. And adds, -8 plus 10 is 2. Multiplies, 2 times 2 is 4. And adds, it doesn't subtract, it adds. And you get 8. You get a remainder of 8. And this says, okay, this would be 4x squared plus 5x plus 2 plus 8 over, don't get confused, your factor's not x plus 2. X would equal 2. X minus 2 equals 0. Your factor is x minus 2. That is what your quotient would be if you divided. Let's see. I think that's about all that I want to tell you. That's what you do when you have this, this remainder and how you represent that. Could you write it? It's a little awkward, but you could. If you had to write this as a sort of factored form, you could still write x minus 2 times your quotient, but it gets really awkward and that's not going to help you at all with any further factoring. So I hope that makes sense, and I'll see you for another video.